Hello everyone, sorry for the delay. My name is Leon Timmermans and I'm gonna talk a little about practical cryptography. I'm gonna focus on two main things, that being passwords and asymmetric crypto. My apologies in advance if your favorite crypto topic is not included. I know you have one, we all have one. I have 20 minutes. And actually, I'm gonna spend most of that time on passwords because, like I said, the title was Practical Cryptography, and I suspect that everyone here in the past year has used password cryptography, and most people haven't used any other. I suspect, or at least, can you raise your hand if you have used something else in something you've written? Yeah, fair enough. Yeah. Oh, passwords are annoying because passwords are where the math of cryptography meets people, which means that everything that can go wrong will go wrong, of course. Um, I mean, us geeks, we like to think about various big O notation things about crypto and all that stuff, and much of that just goes out of the window. So yeah, first things first, common sense. Um, a lot of these things I talk about are really about like getting our end of dealing with passwords right. Um, these don't help that much when users' passwords are really crappy, like 123. Um, you probably want some policy on what is a good password or not. Uh, how to decide what is and what isn't, and how strict you should be is a very subjective problem. Personally, I'm not a fan of websites that have like these extremely specific requirements, like you need to have 2 digits, 2 non-alpha numerics, and the blood of your firstborn. Um, um, but but at least suggesting to the user that their password is bad and maybe they should use something better is something I would recommend. There are like lots of libraries that will already do that on the client side. You can also enforce that somewhat on the server side, but I would suggest using that. Also, um, most passwords schemes that are used today are based on the idea of transporting the password from the client to the server and then comparing that to a value derived from the password. Historically, there are also algorithms that send data that was derived from the password over the network, but those all required one to have the unencrypted password in a database. This HTML digest authentication is a good example of this. I think the Windows networking also used to do something like this. This made perfect sense in the 90s when the US had a ban on exporting encryption. It doesn't really make sense anymore nowadays. Nowadays we have good encryption for the transport part, so well, obviously, I almost forgot to say it, so obvious is it, but you really want to use SSL when you're dealing with passwords. Um, how to set up SSL well? I can't explain that in a few minutes. Fortunately, the Mozilla people have set up an excellent have set up an excellent page at their wiki that literally tells you if you need to be compatible with these browsers, just copy paste this thing into your configuration and then you're all set. And I would highly recommend doing that. They have 3 different levels: modern, intermediate, and compatibility. You don't want to use compatibility. That's for Internet Explorer 6, and you don't want to be supporting that anyway. Also, SSL Labs has a really nice website that will test your SSL setup. It will pretend to be various browsers, and it can tell you how secure is this, and also which browsers will this support. And I highly recommend to test all your websites using this tool to know, because often there's low-hanging fruit, and with an easy change of configuration you can increase your security. So, that being said, let's get to the real stuff. A password database. Whenever you're dealing with passwords, you should always assume that your password database will be leaked. Because it will be, eventually. And with a lot of data, well, it's... odds are you will have data you would rather not have seen leaked, but passwords are unique because they tend to be reused. Most users tend to reuse their passwords in a lot of other places, which means that if you leak their password, that they're suddenly vulnerable not just on your site, but also on a lot of other sites, which makes them particularly sensitive. So yes, obviously, and I don't think I really have to explain this, you shouldn't be storing them in plain text. There are still some corporate people who are like, yes, we want things to be in plain text because then we can tell people what their password was and blah 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 blah. So, okay, sometimes this is a business requirement that you can't get out of for reasons that I don't really understand, but it happens.
Solve that problem. Keylogger solves that problem.
Yeah, but you should never you should never store passwords in plain text because if the database gets leaked, then all these passwords will immediately be leaked. As some of you may remember, this has happened on the Perl monks a few years ago. So yeah, now you may think, yes, I should hash my passwords. And at first sight, that almost looks like enough, except that it really isn't. Because there are plenty of public databases to convert the hashes back into original passwords. These are also known as rainbow tables. And for all common hash functions, you can trivially look up, well, like but at this stage, probably all remotely possible passwords are already in that database, and this is adding marginal security. I mean, it's better than nothing, but it's so little that it's still a far stretch from a secure system. The next level of security in storing passwords is salts. A salt is essentially adding a random piece of information that doesn't even have to be secret, but essentially for every salt you get a different result. So if you would add 32 bytes of salt, you would essentially need 4 billion rainbow tables, which really prevents that kind of easy, dumb attack. However, this does nothing to make an active cracking attack more difficult. If someone is literally trying all these passwords by themselves, the advantage of this is mainly that the idea of a salt is that you don't reuse it for other passwords. The advantage of having a salted hash is that you can't attack all the hashes in one go. You have to attack every individual user's passwords to try, is it this password? That is an advantage. It's a significant one, but it's still not enough. And one of the main reasons for this is because common hashes were not designed to be used for passwords. Their common usages have vastly different requirements from what passwords require. And the main problem is that they're fast. They're really, really fast, and this is a good thing for almost any other usage of hashes. But for example, for MD5, this means that high-end graphic devices can do tens of billions of short MD5s per second. Not millions, billions. Because not only is this a fast problem, but it's also an embarrassingly parallelizable problem. It's just GPUs are specialized in doing the same operation like 1,000 or 10,000 times at the same time, and this is exactly what you would do here. Actually hashing MD5 is a common benchmark for GPUs nowadays. So yeah, this for any common passwords, you can just like go through the entire dictionary and then all various variations, and you'll get a large percentage of the passwords in like seconds. Well, depends on the number of hash salts you have, but still, you can still very easily attack a lot of passwords. And hence, a salted hash is not enough, which is why you need a KDF. A KDF is essentially a function to turn an arbitrary length, low entropy density inputs into a fixed length, high apparent entropy outputs. Again, like I said, this is not really about big O notation. Ultimately, this is about making the constant factor in front of it astronomically large. The only officially standardized KDF is PBKDF2, which is really nothing more than putting a hash in a loop, adding a counter to it, and that's it. It's just common values for the iteration nowadays are I think anything between like 10,000 and 100,000. We're just slowing down the attack by like orders of magnitude. It's not making it impossible, but it's making it a lot harder. And another algorithm that's often used that many of you may know is bcrypt, which is actually a bit of an older algorithm by now, but it has withstood the time quite well, which is it's developed by some OpenBSD people and derived from Blowfish. This again is a function that has an argument for how expensive is this. This is why it has aged so well. Over time, that argument has been increased, but the general concept has been able to remain the same. But yeah, Blowfish was essentially the state of the art in the 90s in this field. Blowfish was really the first that was really designed for this purpose. However, in the past decades, some serious improvements have been made, because especially PBKDF2 and to some extent is still vulnerable to like a GPU-based attack. Blowfish less so. It is still vulnerable to ASICs, which is only something like state agents and big organizations can do, but still it's vulnerable for massive attacks. So that's why a few years ago scrypt was invented. What scrypt introduced was not having only a parameter that for CPU costs, but also one for memory costs. Because even if you can relatively easy distribute CPU costs, you can't parallelize an algorithm that takes like megabytes or even gigabytes of memory. I mean, like the GPU just would not have the memory input-output for that sort of operation. So scrypt was really the first to introduce this idea. It was the first to introduce this idea. It has some flaws in how memory hard it is. It's not as memory hard as intended, but was also the first to try to do it. So in that sense, it was logic. Unlike most other fields of cryptography. Generally in cryptography, you want to be very conservative. problem with KDFs is that it's such a young field that like successive generations really add new things and become better and better and better. So in 2013 there was the so-called password hash competition, and this was won by an algorithm called Argon 2. Argon, which is right now basically the thing that many organizations recommend, because much like Scrypt, it was designed to be CPU and memory hard. And unlike Scrypt, it really is that memory hard as far as we know right now. It has two variations. One is Argon 2D, which is mainly useful for things like cryptocurrencies, which is really intended to be as expensive as possible. And there's Argon 2I, which is now you may wonder, why would I not want that? That sounds great. That sounds good. Except Argon 2I is optimized to be it's almost as expensive, but it's optimized to be side channel free. What does this mean? Well, yet another kind of attack on passwords and other algorithms. That is, a lot of algorithms, the inputs can affect the timing or other traits of the computational process. RSA is specifically vulnerable for this, but there have been attacks based on acoustics of like smart card things, and to gain information on like what is the secret key. And so Argon 2I is really optimized to be entirely side channel free, which is beneficial for password security, even when it isn't beneficial for some other problems. So yeah, all of these have parameters, and I can't really tell you what the right parameters are for you. When you set up a system like this, you really have to experiment with it. Higher is better on one hand, but for example, if you would use like disk encryption, then it's perfectly sensible to use a gigabyte of memory and 3 seconds of CPU time. Whereas on a website, this is going to make your website very DOSable, and you really don't want to do that. You want a relatively short amount of time, so that it doesn't become a vulnerability. So you really have to think with it and play with it and figure out what are the right values for me, because they will be different for different people. To some extent, you can prevent that DOSability using a proof of work, which is basically an algorithm that's much easier to check for generating the value is much more expensive than checking the results. Hashcat is the best known example. It's basically like, this is the start of a message. Now finish it in such a way that it starts with 20 zeros. The binary value. And that way you can easily, that will be like a million times more expensive to generate than to check. And that way you can prevent DOSability, because you're making the client do a lot of work too. So even if you spend a lot, because the client spends just as much CPU time as you, it's much harder, or more, you should do more, it's much harder for them to DOS you. So yeah, and like I said, these are often used for passwords, but they're actually more generic, and they can be used as an input for symmetric algorithm, to have a good key for symmetric algorithm to further encrypt stuff with. Okay. Next subject. I'm going to also talk a little bit about symmetric crypto, because I also think this is a very practical subject that, in my opinion, is rather underused in a lot of, among others, websites and other places. For example, this would be my for me, a good example of where would you want to use that in a place where a lot of people here would need it. How would you deal with credit card information? Because sometimes you need to store that sort of sensitive data, but if your database gets leaked and your websites get leaked, you don't want them to be able to read it. And this is where symmetric algorithms come into play. What you can do, for example, is have the payment. Well, you should have your payment processor isolated from your website anyway. But then you. Oh wait, sorry. The order of things got messed up. Right now, there are, like, as far as I know, on CPAN 2 modules that can handle this for you. The first is script OpenPGP, which implements PGP, as you know. The other is crypt ECDHES, which was written by yours truly. Yes, the former is standards compliant, but it's kind of old standards, and it's a really heavy module implementing an old, not so good standard. So I'm just gonna plug my own module here, because oh, I have to be really quick now. Yeah. Yes, which is basically based on Curve 25519 and AES. Why these are currently very popular primitives. This is what it's doing is very similar, for example, to what the Signal protocol does. And essentially, this means that you just encrypt it with a 32-byte public key and can decrypt it with a 32-byte private key. And if you have a public key on your website and like the private key on your payment processor, then you can securely communicate between those two. And even if everything gets leaked, you're not leaking that credit card information that you don't really need for the website anyway. If your website can show the user their credit card information, you're kind of doing something wrong. But I now have to end this presentation. Thank you for listening to me.